Hi, today we're going to go over the Machine Learning Coursera course, Practice Lab Neural Networks for Handwritten Digit Recognition. We're going to use a neural network to recognize the handwritten digits from 0 to 9. First, we're going to import our packages, NumPy, Matplotlib, and TensorFlow. This week, we used a new activation function called the ReLU, or Rectified Linear Unit Activation Function. This code shows us the three common activation functions, linear, sigmoid, and ReLU. And we can see what the ReLU activation function looks like over here. It's a linear function that goes from 0 to 1, and it is different than the sigmoid activation function we used in the previous lab. Now we're going to go over the Softmax function. A multiclass neural network generates n outputs. We select one output as the answer, and in the output layer, we're going to feed it into a softmax function, and we're going to code that softmax function right now. This softmax function converts z into a probability distribution between 0 and 1, and we're going to sum the outputs, and the outputs will sum to 1. Now, what does this mean? It means that in the output layer, the last layer, we're going to have, in this example, 10 different units. The first unit is going to tell us that the probability of it being the first unit. So maybe it'll be the probability that the digit is a 0. And the second one will be the probability that the digit is a 1. And so on. And the softmax function can be written in this way. Now let's create a NumPy implementation. So first, we're going to calculate the bottom, which is going to be the sum of all the e raised to the z's. Then we're going to calculate and set the top part. We're going to set each of the activation units to be equal to e raised to z j divided by the EZ sum. So first, we need the length of the arrays, and we need the output array, A, and we'll set to a blank array for now. Set EZ sum to be 0. And then we're going to iterate through our array and set EZ sum and increment and keep adding to it the values of each of the e raised to z i's. Then we're going to set each of the activation units. A bracket j will be equal to np.exp of z bracket j divided by EZ sum. And we can see that all tests passed. Next, we're going to vary the z's. And we can notice that the exponential in the top part of the fraction magnifies small differences in the values. So we see that A3 is much bigger than A2, and A2 is much bigger than A1. A1 is much bigger than A0. Now we're on the neural network section. Last week we used a neural network to do binary classification, and now we'll do a multi-class classification. So problem statement is recognizing 10 handwritten digits from 0 to 9, and this is widely used today, from recognizing zip codes or recognizing amounts on bank checks. We're going to load our data set into variables x and y. Then we're going to view our variables. So the first element of x looks like this, and the first and last elements of y look like that. Then we're going to check the dimensions of our variables, and we can see that there are 5,000 training examples. Then we're going to visualize some of our data. And it looks like that. And it looks like it has been labeled correctly. So model representation. We're going to use a neural network that looks like this. We have two dense layers with ReLU activations, followed by an output layer with a linear activation. And finally, we're going to apply a Softmax separately. So first, we're going to code these three layers. This is saying the input layer that's to be specified. Now they're saying that numerical stability is improved or the model is better if the softmax is grouped with the loss function rather than the output layer during training. So we're going to apply the softmax after we're done with training. And we're going to indicate this softmax function by including from logits equal to true later, and loss equals this. Now we're going to code our model, the 3-layer network. So first we need the input amount or the input size. So this is what the input layer looks like. And there are 3 layers here, and we have 2 ReLU layers with 25 and 15 units, and 1 linear layer with 10 units. And so we're going to code that right now. (25 units) activation is equal to ReLU, and we can even specify the name as well. We can say that it's L1. The next has 15 units and it will have the same activation, ReLU, with a name of L2. And the last layer will have 10 units with an activation of linear and a name of L3. And the model looks like that. All tests passed. Now we can examine the number of elements in the weight and the parameters. So the shape looks like that. Now we're gonna compile and fit our model. We're using a sparse categorical cross entropy loss function and indicating that the softmax should be included with the calculation by adding from logits equal to true. We're going to use the Atom optimizer with an alpha learning rate of 0.001, and we're going to fit it with 40 epochs. This is describing that each epoch is the entire data set. So we're going to run our model 40 times. 40 times through our training data set. And we see that the model is working pretty well because the loss function is decreasing with each step. And this is a graph of our loss function, and we see that it's decreasing exponentially. So we're going to make a prediction on an image of a 2. And we can see that there's a 77% chance that it's a 2. And it is the largest output. And now we're going to run it for a random sample of 64 digits. And we can see how many errors we have on this data set. And we see that there are 15 errors, and some of the errors look like this. So for example, this one, the predicted, or the y hat, is a 1, but it's actually supposed to be a 2. And I think that it looks like a 1, but I guess the people who labeled this sample said that it was a 2. Now this one actually looks like a 3, and the model predicted it as an 8. And we are done. Thanks for watching.